This slide illustrates the difference between heating and cooling curves. In graph A, we see a heating curve. It shows how temperature changes as a substance is heated over time. Starting from point A, the temperature rises until it reaches point B, where the solid begins to melt. From B to C, the temperature remains constant as the substance undergoes a phase change from solid to liquid. Once melting is complete at point C, the temperature rises again until the liquid reaches its boiling point at D. From D to E, the liquid starts boiling and remains constant as it turns into gas. After boiling completes, the temperature rises further as seen in segment E to F. In graph B, we see a cooling curve, which shows how temperature decreases as a substance cools down. Starting at P, the gas cools until it reaches point Q, where condensation begins. From Q to R, the temperature stays constant while the gas turns into liquid. After condensation completes at R, the temperature drops again until the liquid starts freezing at point S. From S to T, the temperature stays constant as the liquid turns into liquid. Once freezing completes, the temperature continues to drop as seen from T to V. To differentiate, a heating curve shows temperature increasing with time during phase transitions, while a cooling curve shows temperature decreasing with time as substances undergo phase changes. This is the heating curve of water, showing how the temperature of water changes as heat is absorbed over time. Starting as a solid state, as heat is added, the temperature rises until it reaches 0 degrees Celsius, where melting occurs. At this point, ice and water coexist as the solid turns into liquid, but the temperature remains constant during this change of state. Once all the ice has melted, the liquid water continues to heat up until it reaches 100 degrees Celsius, where boiling occurs. At this stage, water and steam coexist, and again, the temperature stays constant until all the liquid turns into gas. After boiling is complete, the temperature rises again, and the water is now fully in the gaseous state. This heating curve of water highlights the phase changes as heat is absorbed. The green text explains that the heat absorbed during these phases is used to increase the average kinetic energy of the water molecules. This is what causes the temperature to rise in the other segments of the curve. But during change of states, that energy goes into overcoming intermolecular forces of attraction instead. This heating curve of water shows how water changes states as heat is absorbed. At 0 degrees Celsius, the change of state from solid to liquid occurs, melting. During this process, the temperature stays constant because the absorbed heat is not increasing the kinetic energy of the water molecules. Instead, it is used to increase the distance separation between the water particles as the ice melts. Similarly, at 100 degrees Celsius, boiling occurs. The temperature again remains constant while the absorbed heat is used to increase the distance separation between liquid molecules, allowing them to become gas. In both changes of states, the heat is used to separate particles rather than increasing their kinetic energy, which is why the temperature remains constant during these transitions. This slide illustrates the heating curve and the different states of matter during heating. As a solid is heated, the particles gain kinetic energy and the temperature rises. When the solid reaches the melting point, the heat is absorbed to overcome the forces of attraction holding the particles together, causing the solid to melt into a liquid. During this change of state, the temperature remains constant. Once fully melted, the liquid heats up, and the particles move faster as they gain more energy. At the boiling point, the liquid begins to turn into gas. Again, the temperature stays constant as the heat is used to overcome the forces of attraction between liquid particles, allowing the change of state to gas. After this change of state, the particles are free to move, and the temperature rises as more heat is absorbed. This slide shows the cooling curve of water, illustrating how water transitions from gas to solid as heat is released. Starting from steam at 100 degrees Celsius, the temperature decreases until it reaches the boiling point. Here, the change of state from steam to water occurs, and the temperature remains constant as steam condenses into water. Next, the liquid water cools down. At 0 degrees Celsius, the freezing point, the water begins to turn into ice. Again, the temperature remains constant during this change of state as heat is released while water solidifies. After this change of state, the temperature of the ice continues to drop as heat is further released. This slide illustrates the cooling curve of liquid naphthalene. Starting at point A, the liquid naphthalene cools from 90 degrees Celsius to 79 degrees Celsius, as shown in the sloping section AB of the curve. At 79 degrees Celsius, the freezing point is reached and solidification begins. In the section BC, the temperature remains constant during the change of state as the liquid turns into a solid. Even though heat is being released, the temperature does not drop as all the energy is used for solidification. All the naphthalene has fully solidified at point C. The temperature begins to decrease again, shown by the sloping section CD, as the solid naphthalene continues to cool. This diagram presents a cooling curve where we need to fill in the blanks with the correct state or change of state. Starting with point 1 and 2, we see the substance in the gas state. As it cools, we reach point 3 where the substance becomes liquid. At point 7, we observe a gas to liquid change of state as the substance condenses. The temperature remains constant during this transition. As cooling continues, we see the change of state from liquid to solid at point 8, completing the cooling process. As it cools, we reach point 5, where the substance becomes solid. The illustrations F, G, and H represent the arrangement of particles in the gas, liquid, and solid states respectively, with F showing a gas, G showing a solid, and H showing a liquid. summarize the key points covered in this chapter. First, we discuss the properties of each state of matter, solids, liquids, and gases covered in slides 1 to 8. Next, we describe the changes between different states of matter, which are detailed in slides 9 to 17. Finally, we explore the heating and cooling curves of matter and how to identify changes of states using these curves, which can be found in slides 19 to 26. For further examples, refer to the tutorial questions. As we conclude this chapter, here's a fun challenge. Can you explain the magic behind the love meter? Use the QR code to check out this fascinating observation and see if you can figure out how it works. This brings us to the end of Matter 1.1. We have covered the properties of different states of matter, changes of state, and how to interpret heating and cooling curves. Make sure to review the key points and examples for a deeper understanding. Thank you for following along and keep exploring the amazing world of physics.